Welcome to episode 60 in our Let's Play series for Space Engineers Survival. Um, I have got the orientation stuff working. Um, Soon my game stops lagging. So I can turn away from the SIC waypoint, turn the programming block back on, and it spins me right back. I am doing that without touching the mouse. If you watch the bottom there, it is turning on the override controls and setting the override on the gyroscope. There's definitely still some work to be done here. So this is going to be a code review episode, and keep in mind that this is not finished. I'll go ahead and post it, I guess, up on the GitHub, but just keep in mind that it's definitely going to change. It's nowhere near where I want it. So this is the scripting block for the cargo shuttle, so it's got some of the other stuff for that in here already. We've got a constant that is it's not noted as a constant, but it is, which has the waypoint in it, and that's just a copy paste from the GPS screen here. And we've got a waypoint to hold that once it's parsed. We've got, this is actually not necessary. I did this just testing something that doesn't actually seem to work at this point. This find all method, it's a static method on the waypoint info class. I'm not really sure what it does or how it works. It would make sense if it was actually going to be getting you all of the waypoints that are stored in your terminal, but that's not what it does apparently. There's a parameter here that's called source, but the API documentation doesn't actually say what it's supposed to be. I actually posted a question on the API GitHub to see if somebody could tell me how that's supposed to work, but I haven't gotten an answer yet. So anyway, that's not actually useful code at this point. Maybe someday it will be. But all this stuff is just, or this stuff right here anyway, is adding the prefix to the terminal blocks. If it's not connected, then it doesn't do it. Get the prefix, which is something that I stored on the programmable blocks custom data. The code for this is also on the relay satellite, so this is all familiar stuff. This is literally copy pasted from that. Now I've done something a little bit unusual here in that I set the update frequency to 1. So it happens every 1 tick, and that's kind of necessary for the autopilot controls. Otherwise you're going to end up overshooting your heading and needing to correct and correct and correct and correct, and I don't know that it'll ever actually fall to center. So we're updating on update 1. Anyway, the way this was working, and this is a little bit complicated, this is going to be a math-heavy episode, which would probably be implied from the title, involves the law of cosines. So if you're not really into the math and are not going to be able to understand it, then I apologize for that. I'm going to try to keep it as simple as possible, but we'll see how that goes. I'll try to cover the simple stuff, and if you just want to copy paste something and use that, great, but I'll try to explain it as well. Anyway, we're grabbing our remote control block because this is what everything's going to be based around, and right now I'm just pulling it by name. When I update this and get it working how I actually want to, then it won't work that way. It'll be slightly different. I'm also getting the cockpit main LCD panel just so that we can output some information. We're not actually doing anything programmatically with this except for displaying stuff. Then we declare 2 doubles for pitch and yaw. This is how much we need to alter our pitch, how much we need to alter our yaw. Then we call this get direction to method that I pulled the original version off of the forums, the Keen forums, but I think I reverse engineered it enough and altered it enough because I actually do sort of understand what's going on there. It's still basically the same, but some things are a little bit simpler. Pass in the GPS coordinates you're heading to, the terminal block that you're calling your origin, which is going to be our remote, and then you set output variables for the pitch and yaw because we need to return both of them, and it's not possible to return 2 values unless you put them in an array or something, but this is just the way it was written originally, so I kept that. And then we're displaying those values out to the LCD panel in the cockpit. And here's where we do the actual work. Grab the gyroscope. Again, we're just grabbing it by name. That'll change eventually. Turn override on. Now, if the absolute value of the change in pitch is above the attitude max, then we're going to cut it down. We're clamping it basically because even when we're on update 1, it still tended to overshoot if it was spinning too far. Like if you were turned all the way around behind it, it would overshoot and then need to correct. But if you clamp the value down so that it doesn't go above, we have it set to 20 here. It's pretty reliable and gets you there without overshooting. So these two are just clamping it. If the absolute value, because this could be positive or negative when it comes back, this get direction too. So we want the absolute value, and if it's bigger than the attitude max, which is the maximum speed that we want to put on the override, then we will set it to the maximum and then multiply it by the appropriate direction to flip the sign. So if pitch is less than 0, we multiply by -1. If it's greater than 0, we'll multiply by 1. Do the same thing for yaw. And now here, if the absolute value of the pitch is greater than the tolerance, and the tolerance is a very small number, it's basically how far off we're willing to be, because even, again, on update tick 1, it's not going to be perfect. So that's how far we're willing to let it be out of whack. And this is kind of a separate thing down here too. So this is doing, if the pitch is greater than the tolerance, then set the pitch on the gyro to pitch times attitude rate. And attitude rate, the point is to make it smaller, because even if the max is set here to 20, it still moves pretty fast. So if you reduce the rate there, it will go a little bit slower. Now you can tweak all these numbers. I found these numbers to be pretty reliable and not overly slow. So these are the numbers that I'm using for now. Those are subject to change. Anyway, here we're setting the pitch, and you'll notice here that we're setting using the yaw value to set the gyro's roll override, and that is because yes, I do want to remember changes. I didn't make any substantive ones. Go ahead and recompile that just so that it's running the current version. But if you look back here at the gyro, the base is not pointed down. The base is pointed towards the front of the ship. So when the gyroscope is rolling, it's yawing the ship. When you're actually using the controls from the cockpit or even from the remote control block, it uses the ship's orientation. But if you're setting the gyro override, it uses the gyro's orientation. And that's probably the first fix that needs to be made to this script, really, is getting it to adjust which value it sets here based on the orientation of the gyroscope. So that's going to be my next trick in terms of getting this to work correctly and be a little bit more general purpose than it is at the moment. If you're trying to copy paste this based on the version that I put on the GitHub for right now, which hopefully won't be there by the time this video is uploaded, but we'll see. You might have to monkey with which one of these you're actually changing. If it is inside the tolerance, then it sets it to 0, so it's not doing anything. And here, if the yaw and the pitch are both within the tolerance, then turn off the gyro override and return control, theoretically, to the player. But as long as the programmable block, at least at this point, is turned on, it'll be doing this. So I will also have to set this to something that you can, pass in an argument, turn it on and off, and have the rest of the programmable block still be functional, even if the autopilot is turned off. So now we get into the math. This is complicated. It took me a little while of looking at it and reading some Google stuff about trigonometry and whatnot to figure out exactly how it is that it was working. I was under the mistaken impression. I mean, there might be a way to do it this way, but this is not the way it was done. Using the forward direction. That's how you get the forward vector from the remote block in this case, which is our origin that gets passed in. This tells you the forward direction, this tells you the up direction, this tells you the right direction. There's also, obviously, back, down, and left. But I thought it was using the forward direction. Turns out the way to do it, at least that I'm familiar with now, is using up and right primarily. And some of you, hopefully most of you, have at least heard of the Pythagorean theorem before, a squared plus b squared equals c squared. Significantly less well known is the law of cosines, which is basically the Pythagorean theorem, but there's one extra term that when your main angle in the triangle is not 90 degrees, you can use that still to find the length of the sides and stuff like that. When the angle is 90 degrees, that term effectively becomes zero, and it becomes a squared plus b squared equals c squared. What the law of cosines is that a squared plus b squared minus 2ab cosine theta equals c squared. And that minus 2ab cosine theta, the theta there is the angle that is usually a right angle in a right triangle, where you use the usual Pythagorean theorem, and the cosine of 90 degrees is 0. So 2 times a times b times 0 is always going to be 0. So that term effectively goes away, and it's just a squared plus b squared equals c squared. But when that angle is, 20 degrees or 140 degrees or anything other than 90, then that cosine theta is going to have a value. And a squared plus b squared minus 2ab cosine theta will give you c squared still. Now, when we go through here, we are actually figuring out the length of a, b, and c. So we know a squared, we know b squared, we know c squared. What we don't know is theta. We don't know the angle between the up vector and the vector to our target. We don't know the angle between the right vector and the vector to our target. And those are what we need to figure out to get the pitch and the yaw to turn it so that those angles become 90 degrees and we're pointed straight at it. We're trying to zero out that turn, basically. That's the goal, is to make it so that the pitch and yaw that we need is 0. So 90 degrees from right to the target, 90 degrees from up to the target. Up being pitch, right being yaw. So what we do is we get the position of the origin block, the position of the remote block. We get the position at the tip of the forward vector, the position at the tip of the up vector, the position at the tip of the right vector, all based off of the origin, because just this is always going to be just a unit vector of length 1, pointed off in some direction. It's not actually going to be the location in space. It's going to be kind of a guide your location relative to this block. So if you want it in space, which is where the target is based off of, is in space, not off of your ship, obviously, then you need to add the position of your origin block. I hope I explained that clearly. If you have any questions, please by all means hit me in the comments and I'll try to explain better. So the next thing we need to do is figure out the length of the sides of our triangle. So this is going to be, basically this is A, or B, however you want to look at it, one or the other. But this is the length of the vector from our current origin position from our remote block to our target. So the distance from the remote block to the SIC waypoint here. This is the distance from the target to the tip of the forward vector. This is the distance from the target to the tip of the up vector. And this is the distance from the target to the end of the right vector. So now we have the sides of all three sides of both triangles, because the origin to the target is used in both of them. And then the origin, no, I'm sorry, the target to the tip of the up vector, or I'm sorry, no, I'm confusing myself here. This is why this is 1 here, because I replaced this. In the original function, it did actually calculate this out and used a variable, but it's always going to be 1, because this is the length of your directional vector from the origin, and that's the whole point of it, is that it's a unit vector, so it's only 1 meter in all cases. So that's the other side of the triangle. And then the one that we're trying to shorten and get to make the angle right is the distance from the tip of that vector to the target. And that one's going to be the one that varies as we rotate. So like we're rotating around the origin block is the idea. I don't know that it actually works that way with the gyros, especially if they're in override mode, but it's basically like that. So this is where we're doing that target to the tip of the front vector. We don't actually use this for calculating the triangles. We use this because you can get the same triangle, or at least the same angle, with yourself pointed more towards the target or with you pointed more away from the target. So this is used to figure out which one is which. If the origin is closer than the tip of the front vector, you're facing the wrong way, and you need to turn further. If the front vector is closer to the target than the origin, then you're facing the right way and you don't need to turn quite as far. And that's corrected for down here, and we'll get into that in a minute. But here's where we're actually getting the length of the sides. Again, we know how long the unit vector is up, we know how long the unit vector is right, but we need to know how far the tips are from the target. So we're getting the length there. So now we've got A, we've got B, and we've got C. Oh, I'm sorry, no, we've got A. We know B because B is just this unit vector. That's always 1. And we've got C. This is C for pitch. This is C for yaw. So then we take that law of cosines function that I mentioned earlier, and this is where some algebra comes into it. And this was all done for me on the forum thread, but I did, confirm it by learning the law of cosines and following through the algebra solution, where you basically solve a squared plus b squared minus 2ab cosine theta equals c squared. Solve it for theta. And that comes out to the arc cosine, which is, basically you put in a cosine value and it gives you back the angle of a squared minus b squared minus c squared divided by 2 times a times b. Now a is 1, or b is 1, whichever one you want to use, so multiplying by 1 doesn't do anything. Again, that term was actually here in the original code, but I just dropped it out because it's always going to be 1. So minus 2 times b, or a, however you want to consider it, and that's going to end up giving you theta. And since we're going with the up vector here, that's going to give you theta p for pitch. We're going with the right vector here, that's going to give you theta y for yaw. Now this comes back from the math.acos function in radians, so it has to be converted to degrees first of all, which is what's happening here. And then, what is this doing? I know what it's doing, I just have to remember. Oh, it's converting it from the direction for the up vector to the direction for the forward vector, because the angle between up and forward and right and forward is 90. So when you take 90 minus theta p or theta y, it's going to give you the angle that front needs to turn, because otherwise you'd be targeting getting this to 90, I'm sorry, this angle to 90 degrees and this angle to 90 degrees, but that's not really what we want to do, because we're feeding these values directly into the override for the gyro, so we want 0 to be your on point. So that's why we do this 90 minus here, so we can convert it and basically say, okay, if the forward vector is pointing towards the target, that's when we know we're done. So that's what that 90 minus does. Now this is the one I was mentioning a little bit earlier about, if the target is closer than the forward vector, or if the origin rather is closer than the forward vector, that means you're pointed in the wrong direction, because the forward vector is going to be further away than the origin. So you do 180 minus the pitch. Same thing for the yaw, 180 minus the yaw. And that just basically is reversing the angle, because you can get the same theta, the same pitch, the same yaw. You can get the same number whether you're pointed forward or backward. The only way you can tell the difference is based on that forward vector there. So that's what that is correcting. And then this is turning it from, 220 or degrees or 270 degrees or whatever to minus 90 degrees. So instead of always turning the same direction and going all the way around, you can turn either direction and make the shortest turn possible to get to where you want to go. And then we set the return values, and they come back here, get displayed out to the LCD panel, and then we do the gyro override stuff. So I tried to explain that as well as I could. at least, at this particular point in time. I'm not sure if there's any particular way to make that easier to understand. Um, but again, if you have questions, by all means ask. I will post the link to the forum post that had the original code that I stole and then made some modifications to. It's very old. I don't even know if the guy who posted it plays the game anymore. It was Cheetah something or other. So props to him for, posting this if he ever watches it. Thank you. Um, I also did some Googling on the law of cosines and exactly what that means and how that works and why that's true and how it gets figured out and how you do the algebra to solve the default a squared plus b squared minus 2ab cosine theta equals c squared thing. Solve that for theta. Um, I mean, it's not overly complicated algebra, but it's been a while since I did it, so it was nice to have a guide to kind of explain that. And I mean, it all kind of came back to me as I was doing it. So I'll include that link as well. As usual, I will put the links to the in-game script API and to my GitHub, and I will put this up on the GitHub if you want to steal it without pausing the video over and over and again to type it out yourself. Um, and again, if you have questions, please by all means post it in the comments. I'd be happy to try to explain anything further if I can. Try to help you understand it better. But that's really all I have for this episode, is to demonstrate that and go over the code. My task for the next episode, and hopefully I'll be able to figure it out and get it done in time to post it, is to figure out how to modify these values based on the gyro's orientation. Because you should presumably be able to just stuff all these numbers into a vector and then say gyro pitch equals vector x, gyro roll equals vector y, gyro yaw equals vector z. Um, but you have to have the vector basically oriented appropriately for the gyro to do that. And I've seen code to do it again, but I don't understand it, and I am hesitant to just copy something that I can't then explain on video. And be like, this is doing magic and it works because it works, so congratulations. So yeah, I'm going to try not to do that. I'm going to try to actually understand it and rewrite it a little bit. I mean, this is pretty much exactly what was posted on the forum. Like I said, I did make a couple of changes to it, mostly in code organization and a little bit in like the numbers here. Like I said, this is always one. This used to say, um, which one was it? Oh, this was OVUV, which is not a variable I don't even have anymore. Because OVUV, first of all, is just the exact same thing as this, because OVUV is UV, or OV rather, minus OV, which is the exact opposite of what we just did here. And like I said, these units or these vectors always work out to being a length of 1. Like that's the whole point of them, is that they're unit vectors that give you a direction without bothering with the magnitude, because the magnitude is not important. If you've seen Despicable Me, you know that a vector is direction plus magnitude. Oh yeah. Yeah, so that's like the guy's thing in Despicable Me, the bad guy, the real bad guy. After Groot decides he's a good guy. Um, but yeah, so like there's no point in having the magnitude here because you don't care about how far it goes. You're really only interested in the direction. So these are what's called a unit vector. They're always length 1. So if you're taking OV back out of this, this is always going to be 1. 1 squared is still 1. So there's really no point in getting the vector and getting the length and messing with all that if you're just going to put 1 in. And then the same thing here, because that was the other side that we used. We don't use C here, and C is this one. But if this is 1, then multiplying it by 1 doesn't do anything. So I took that out as well. And then I rearranged this stuff so that the actual steps that we were doing were together rather than pitch being together and yaw being together, just because I felt like it was easier to kind of follow, as we transformed each value along the way to get to where we needed to go. But I'm calling the fact that I made any changes to it at all proof that I mostly understand it. I'm not saying I could come up with it on my own. Again, big props to the guy that did. The player that did. Shouldn't be assuming people's gender, sorry. But yeah, so that's what that is, and that's all going to be posted. And hopefully I'll be able to make those improvements so that we know what the gyro is doing. I also have a longer term plan for more autopilot stuff, and this is going to be a pretty big project, so it's definitely going to spread out over a number of episodes, and we'll try to get some regular building done in between. But not only do we have to find the orientation and override the gyros to do it, which we've done, we also have to correct for the gyro orientation, which we're going to work on next. The next thing we have to do is identify all of our thrusters and which directions they're pointing so that we can override thrusts in the correct direction to get us actually moving towards the target that we've selected. We need to figure out how much acceleration we have, force of the engines, um, divided by mass, because that's F equals ma, using some physics function formulas here now too. Force equals mass times acceleration. So if we want to get acceleration, we need to divide force by mass. We can get our acceleration so we can figure out when we need to start stopping, so we don't overshoot our target. And that's just the very basics of navigation. We're also going to want to figure out how to do some basic obstacle detection so that if we're about to hit an asteroid, we can move. If we're about to hit a satellite or something, we can move. If we're trying to go somewhere on a planet, maybe even. I mean that's kind of a little bit ambitious, I think, since planets are so big. To route around them would be a little bit difficult, but we'll shoot for doing that as well. Like I got some ideas here, some big ideas. This is going to be a pretty general purpose autopilot thing here. Something I forgot to write down, and we would also like to do at some point, is manage gravity. Just writing that down now. Because the way that this is written right now, this will only work in space, because the idea of correcting for gravity is not really a thing that's part of it. And I would like it to be able to do that as well eventually. I can get all the resources that we need from asteroids and stuff. Going down to planets is kind of, if we're doing that, it's mostly doing it for fun, and doing it on autopilot is not really a necessary thing. But again, I'd like to have a very general purpose thing. And what is it? Sam's AutoPoint or Autopilot Manager, I think is what it's called. That's exclusively for working in gravity, if I remember correctly. I think he might have expanded it since then to work in space as well. But the review that Splitsy did of it, it was purely a planet side thing with gravity. So I know it's possible. I know it can be done. So that's something that I'd like to add as well. And then beyond that, and this is where it starts to get fancy, um, I want to have it figure out what the connector's orientation is if it's flying towards the connector to dock with it, so it can orient properly and actually dock. So we'll have to find not only the orientation of the connector we're connecting to, but also the orientation of the connector on our ship so that they line up properly. And then this is where it gets really fancy, and I think this will be cool. I want to use the intergrid communication thing to basically send out a broadcast that says, hey, I'm looking for a docking port that meets certain criteria, whether it's a docking port that has access to cargo, or a docking port that's on a certain ship or in a certain area or whatever, and then have if there's a grid that meets those criteria, have it reply back and say, hey, you can come here, and then it will automatically lay that into the autopilot and send it off on its way. So we can basically have an automated inventory that includes cargo drones flying around trying to find stuff and pick stuff up. So the SIC is short on um, ice, for example. It would be able to fly out to Ice Station 1 that we have, dock up with it, collect a bunch of ice, bring it back, unload it. I think that'd be really cool, and I think that based on what I know of intergrid communication and this autopilot stuff so far, I think it's something that we can manage. But that's definitely advanced level autopilot stuff, and like I said, this is going to take quite some time to get done. So please subscribe to see if we ever get there. I may end up losing interest in this series far before that. But I hope not. I think that would be fun to do, and pretty cool to get set up. Um, Other than that, likes, comments, verbal abuse are all welcome, especially comments. Again, if you have any trouble understanding this and you want me to try to explain something in particular to you that I have not explained adequately in the episode, I am more than happy to try. So now, just for fun, I will do this a few more times. Not touching anything, not touching anything. And it just spins right around, back to where it's pointing there. And this is a little weird. I don't know if this is because of the autopilot thing or what, but when I try to go forwards and backwards, I get, the full amount of usefulness out of my thrusters. Or when I try to go from side to side or up and down, I'm not getting proper acceleration. I don't know what that's all about. But if I tell it to go back a little bit and then try to go side to side, it works. And then if I cancel out my forward velocity afterwards, it's still fine. But now I'm moving off to the side, and because the autopilot's turned on, it's going to continue pointing me at that spot. Now I'm just drifting in one direction here, which is also something else I would like to have the autopilot be able to do is, maintain a certain speed or maintain a certain velocity, I should say, relative to the ship. Um, so, if you're moving sideways at 0.88 meters per second, then as the ship turns, it will maintain your speed at that rate. It'd basically be the same thing as turning off the front engines, the forward-facing engines, the braking engines, and keeping inertial dampers on, which is something that we did when we were planet side a few times, so that we could keep our levitation thrusters turned on when we were still using the atmospherics, and it wouldn't slow us down, and we wouldn't have to continue pushing forward to maintain speed, save a little power that way. Um, but yeah, I think that would be a cool thing to have. So we could basically maintain our distance here from the SIC because we're drifting away. Like we're going to continue pointing at it, but we're moving in only one direction. So we're getting further and further away, and eventually we're going to be, facing directly at it from the side. But yeah, so like I said, I got ideas, and we'll see how many of them end up coming to fruition before this gets to be too much to deal with. But I think I've gone over everything now, so thank you very much for watching. I've already done my likes, comments, and verbal abuse thing, so see you next time. Thanks. Bye.